Let's start today. Welcome to the fourth day. Good morning. And today Christian will be telling us about local vector convergence on Sparse.
Okay, so good morning, everybody. Thanks for getting up that early. So I will talk about local convergence for sparse graphs. It's another notion of convergence, and it's I think originally Remco van der Hofstadt, who has sort of almost written a whole book about it, was supposed to talk about it. And then he couldn't come, and I said, fine, I'll talk about it. But it has, a lot of it has been mentioned. Yegane will use it in her talk this afternoon. So this will, I doubt I will use the hour and a half. Okay, so we'll see, but so you can ask as many questions as you want, because I have a few slides I can use to relate this back to what it would be compared to dense graph convergence, but we don't really need that part. So if we just finish with the stuff I'm doing on the whiteboard because you have tons of questions, that's just fine. Okay, so but before I do the whiteboard, just as sort of context, so we still are wondering when should we consider a sequence of graph convergence, and we have seen that for dense graphs there are many equivalent notions. And so the question is, what do we want to do if we have sparse graph such that the average degree is bounded? Okay, and so it turns out that if you just take the notions for dense graphs and just look at them as they will all be trivial. Okay, so let me give you an example. So if we sample, for example, two vertices uniformly at random from a graph whose average degree is bounded, well, you see the probability of seeing two vertices is the sum of the vertices, the probability that the edge is there. So this will be twice the number of edges normalized. And so you get 1 over n dn bar going to 0. And actually, this is true if you do it like that for any sparsity. Okay, so you certainly have to modify these. You could just divide this probability by something else, but then it's not a probability anymore, and that would actually not work. Okay, so this is the one quantity which you really can't that easily fix. The other ones, there's some fixes, and they sometimes work and they sometimes don't work. But we would like to have some notion of sampling, right? Because there was this very nice thing for dense graphs. As I sample k vertices, I find sort of a k vertex graph. I can then first do my limit as the graph sequence goes to infinity, and then the limit k goes to infinity. I get an infinite random graph. So that's a very nice limit. Okay, so if we, for the moment, forget that they're graph ones, if we try to express sort of a limit of a finite graph, you might just say, naturally, look, a limit of a finite graph should be an infinite graph. Well, that is not quite true. So in the dense setting, we saw it's an infinite graph, but it's actually an infinite random graph. So is there some way to do something similar here? And actually, before we came up with this theory of graph convergence, a person sitting next in my office actually had done that before, and we actually were not aware of it. When we actually were aware of it, we were just too stupid to put it together. But anyhow, we were doing the theory for dense graph as this doesn't apply. But Oded Schramm, together with Itai Benjamini, they actually defined a notion of graph convergence for bounded degree graphs. They actually had it for graphs with bounded degree period. But it actually works much more general. It works certainly for average bounded degrees under some conditions, which I will not go into for the moment. But they just said, okay, so rather than sampling many vertices and look at the induced subgraph, just sample one vertex, look at a given radius r, see what you see. Okay, so you see some random graph, some random rooted graph. And therefore, the limit will be an infinite, possibly infinite, rooted random graph. Okay, so we have this sequence which is locally convergent or Benjamini-Schramm convergent. Aldous had some implicit version of it. So as in many of these cases, Aldous sort of solved the math problem before any of us thought about it, but he didn't formulate the concept. This is another example of that. So the concept is really due to Benjamini-Schramm, But a lot of the mass you might want to need is already in Alvus, who, however, it was more implicit in there. So
who's the person who's in the office next to you?
Oh, that's Sean. Okay, and he actually did that just as he came to Microsoft and we were hiring him. So he even gave a job interview talk about it. Yes.
So you want to solve the sparse graph where the edges, the number of edges is small O of n squared.
Linear in n.
Actually, in this talk, I will just do linear in n.
Linear again.
Jennifer on Friday will do when it's growing with n, but small O of n.
I see.
So in this talk, we do linear in n.
If it is linear, can you just multiply that like that in the limits by n?
So you could, but you end up with a problem. Because, for example, assume we would count, if I have something like counting triangles, okay? Let's say we do G and P. Okay. In G and P, if P is constant over n, then the number of these is just n to the 3 times P to the 3, which is C to the 3. Okay, so the probability, so you have to, so if you translate it into a probability, you can normalize in such a way that this becomes of order 1, okay? But you have an issue because if you look at this guy, what's the number of edges? Okay, the number of edges is P times C. So that's of the same order, is C, okay? And so actually C is larger than 1, C is smaller. So in certain, so huh?
Yeah, you are hiding all the constant, but nevertheless, the number of edges is C times n.
C times n.
Yeah.
Oh, okay. So the problem is, here is actually the problem. Okay. So the number of triangles is C to the power 3. The number of edges is C times n. So what does that mean? Which means by just deleting a tiny fraction of the edges, your triangle count suddenly goes to 0. Okay. And if you just divide in this quantity, which I had there by what you think you should divide, okay, this problem will bite you in the back. It will be extremely unstable. You will get a notion of convergence where if I remove 3 edges, I have a different limit, which is probably not what you want. Okay, so that just doesn't work. And the other version actually does work. So, and I will go on the board. So if you didn't get the definition, I'll do that again. So I will give you a few examples. I will, in this case, actually, we have never talked about random graphs, actually. If you have, or not very explicitly, so all my notions of convergence, you would have to invent what they mean for random graphs, because now actually your sequence is random. And for example, if I sample k random vertices, now I have 2 randomness. How do I deal with both of them? And if you don't do sampling convergence, if you count subgraphs and so on, it's a little easier because, well, you get some random quantity, but you don't have another randomness you could get confused about. And so then you can just say, okay, I have this quantity and that quantity converges in probability or almost surely. And we need to do something like that here, but we have to be very careful because there is this randomness from sampling and there might be an underlying randomness from the graph. And if you don't sort of deal with them correctly, then you can prove no theorems, okay? So that's a little tricky and I will discuss it. Then there is, it turns out, a property. So when we did this sampling k vertices and did the limit, we got an infinite random graph and had a very nice symmetry. It was exchangeable, okay? And that gave us some representation theorem, Aldous Hoover, and it could do a lot with the symmetry. So the question is there some symmetry here? And it turns out the answer is yes, it's unimodularity. And then for graphons, we had this theorem which says, given a graphon, I can always find a sequence which converges to it. So now you may ask, if given a unimodularity limit, which I haven't yet defined for you, does there exist a sequence of graph convergent to it? And that actually, well, if you are sort of not sure you're getting tenure and you solve this problem, then no matter how bad you were before, you'll get tenure, okay? Because that's a wide open problem. I mean, there's some partial results, but it's really open since at least 20 years. And even the famous Aldous wrote a paper which he had to retract because he claimed it's true and it's not true. So there are sort of proofs which are wrong, and we just don't know it yet, okay? So I will do these on the whiteboard, and I might actually use the whole whiteboard. So can we, for the moment, I might even want to use the middle. Okay, so to make actually what I said before really precise, we need a little bit of notation, because it turns out that in this setting, it's really important to think about, well, if I have a rooted random graph and I say something is equal to this rooted random graph, we don't really have equal, we have being isomorphic too. And we have to do that carefully. Okay, so let me first discuss sort of the symmetries we have here. Okay, so we have standard isomorphism. What I will actually need to discuss whole thing is space rooted locally finite graphs. And we need a little bit of structure on this graph to define this notion of convergence. So in particular, we need to discuss what is an isomorphism. So I have a graph. It's locally finite. What I mean by that, locally finite means that all degrees are finite, but they're not bounded. The graph can be infinite. It can look very complicated, infinite graph. But if you look at, and it has a root, okay? So that is root, okay? So now we have a rooted, locally finite, possibly infinite graph, okay? And now I will say that sigma g, let me just write OG, and I will just give the root, no, let me call it O prime, G prime, okay? They're isomorphic if there exists a bijection phi from the vertex set to the vertex set. And now, and two properties. One is the usual one. Okay, is G if I only have okay. Any idea what my second condition will be? Not from the experts. Those who know the definition of local weak convergence are not allowed to answer. Does anybody not know this definition? Okay, so do you have a guess what my second condition would be?
So you should send the root to the root.
Correct. Okay, so phi of the root is root. Okay, so when I sort of just wrote on my slides that the local neighborhoods converge, I mean that they converge if you sort of mod out by isomorphism. Okay. Now it turns out that it's often where I will want to talk about continuous functions. So it's actually
This is the definition of that equal squiggly thing. Yes.
this is the definition of equal squiggly thing, and this says that. Okay, and then we say that sigma g is isomorphic. Other rooted random graph. Okay. So Can I move this one too? Oh, and now I can write on the wall. Good. So now I need a second notion, the notion of the ball of radius r around a point. I think I will not define that. So if you have a graph, you get a graph distance, and the ball of radius r consists of the set of all vertices up to that distance and all the edges which join vertices up to that distance. Okay. So now I will say, now I will define the distance, and it's called the local distance to rooted graphs. And I will just give the roots the same name just to have that. Otherwise, you just need to do this map, which I'm lazy and won't do. Okay, so this is the infimum of numbers such that all of radius r in one of the graphs, sigma g, is isomorphic to the ball of radius r g prime. Okay. So now you may, okay, so why is it maybe a good idea? Well, you know, there's these infinite graphs. And I want to say, well, if they're up to some large neighborhood around the origin, the same up to isomorphisms, it's hard to tell them apart. I have to walk for a long time. And if you imagine having some process on it, the process have to go pretty far. So it might be sense to define those as near to each other. And that's what this does. And you might think that, so that probably means that if the distance is 0, then these two graphs must be isomorphic. Okay. But that's actually not the case. Can somebody imagine why that's not the case?
Question of VR.
So what of BR is a ball of radius r. So this is the set of x g. So this depends on the graph, such that the graph distance, so root and x smaller r, it's the edge set, and then we look at the induced subgraph. Actually use it rooted subgraph. That's it. Okay, you have your graph. Here's a large graph. Here's another large graph. And now the ball of radius 1. So the ball of radius 2 is all these vertices. For you. Including the boundary. Okay, so this is the vertex set, and it's this graph. And this its root.
You're not like embedding this in some 2D space, you just happen to draw a graph.
Just about the graph distance. Okay, so just we have some graph. I take the ball of radius r in the graph, so that's all vertices you can reach by a walk of length up to r. And then you look at the edges you see up to that distance, and you throw out the rest. Okay. And now here I have another graph. This looks like this. Okay. And now if I look just up to this distance, they have to be actually the same. But in particular, they are isomorphic. If I look up one distance more, they actually, the distance, now they're not equal, but they're still isomorphic. But if now I make this one look like that, and this one look like that, then if you go up to one distance more, you see that this graph now has this other wiggle here, and this one doesn't. Okay, so then for these two graphs, the distance therefore, so the minimum, the largest R where they're different, where they're equal is 1, 2. So their distance is. Okay, is that clear so far? Okay. It doesn't really matter that I put here 1 over R plus 1. I could put e to the minus R or whatever. I just want something such that, okay, but.
All right. But inverse to the inverse or reciprocal of something that is closeness, right?
Yeah.
Whatever.
However, this is not, does not mean they're necessarily isomorphic. No, so let's do this again. Okay. So far they look isomorphic. Okay. If the distance is in, so this distance is actually 1 over infinity, so it's 0. Okay. But now I add something to this graph. Just add it.
Do we always start from the root?
You always have to start from the root. Okay, it's a ball of radius R around the root.
It's local.
Okay.
So that's why it's called the local distance. Okay. So the distance between two rooted graphs essentially tells you roughly up to which distance in the graph matrix they look the same, or they are isomorphic. Now, this graph, if I calculate these balls of radius R, this guy is never integral. So with this distance, they still have distance 0. Okay. So this will actually only give you equality for the component of the origin. Okay. So we could actually just define this space as rooted connected graphs. And actually, you might want to think about it like that, even though sometimes it's convenient to have these other graphs too, but just put them all into one. It sort of doesn't matter if they have disconnected components, we will consider them the same because we will think in this metric. And so you might as well choose the connected representative. So think of them as connected. Okay, so if we in addition say locally finite connected graphs, okay, then actually they are isomorphic if and only if this distance is C. Okay, so now we have a nice space. We have this space of rooted, possibly infinite graphs, and we know when they are sort of the same, i.e. isomorphic, and we have matricized in sort of the words of the, I don't know, topologist, this, yes?
When you say connected for these graphs, can there be a difference between a path notion of connectedness and the topological disconnected? Because you could imagine a connected graph where they're parts so far away. But I guess in this definition, so should I worry about that distinction, or does it not?
No, because they're always sort of, okay, if they're infinitely far away, then sort of I don't quite even know what it means. Okay, so because it's in a topological notion, you should think about how we sort of generate our topologies, and we always want to think about the product topology or something like that. So there's no, this is sort of all the trick with all probability theory on infinite graphs, right? You sort of effectively always say, whatever I define, I generate by my finite objects. Even the sigma algebra at infinity in calculation will be, if there's nothing you can define by something which is infinitely erased, this notion doesn't exist. And in ZD, we don't have infinite array, we just have larger and larger balls, and we sort of look at them. So you don't have to worry about it, okay? So now we have this notion of topology, Okay. And now we can just say, okay, so whenever I write this G now, this object, okay, I will sometimes write G local, and I will sometimes think of this as where I factor out equivalence classes with respect to the local. So you always should think of, but we see now if I factor this out, this is just the same as looking at equivalence classes of infinite rooted random graphs. Okay. So two isomorphic infinite rooted random graphs I consider the same. Okay. So now we have a nice space, and it's sort of very intuitively. So it's very near to your intuition. We just want this local neighborhoods converge for each R, and that is captured by that, except you have to look at isomorphisms. Yes?
So I was wondering, for the particular choice of the basis 1 over R plus 1, is there a particular reason for that?
Okay, let's change it. I'll make it 1 over R squared plus 1 because it's okay, let's do that. Or maybe we should do 1 over log star of R. It still works. Okay. So it doesn't matter, okay, as long as it goes to 0, as R goes to infinity and it's monotone, I don't care. So which one do you prefer? I also don't want it to be 0.
Simplest one.
Okay, good. So
So this, like when you say, this is now for random graphs?
no, so far the graphs are
Okay.
Not yet, he will
they're
come.
not yet ready.
So in the bottom line, you're saying that two graphs are locally convergent if,
I've not done
Not
yet
yet.
local conversion. So far, I just have to find to use.
what's this arrow on the last line about?
Oh, this just
Filtering out,
means I will.
filtering out.
This is not a mathematical error. I'm saying I will sometimes write this, and I will sometimes write this, and I will from now on just. You always should think of this rooted infinite graph. If I will talk about a continuous function on this set of graphs, it's with respect to this method.
So if this thing holds for all R, are the two graphs isomorphic? I guess they are.
So yes, so they're isomorphic exactly if and only if this holds, if they're equal for all R, right?
Given it's connected. Given that it's connected.
Given there is connected.
Given that it's connected.
Or he can restrict the set already by passing. If you restrict yourself on the component, the root is contained in. Whatever.
You can do that,
Whatever.
but if you sort of in the end factor out by this equivalence,
Right.
then actually all graphs which have the same connected component of the roofs are considered the same anyhow.
Yeah.
So I may as well, right? I'm only on the graph. I mean, I'm at the root, I'm walking around. The fact that there here is another quantum universe, I don't see, I don't know. Okay. These me as the aliens, but they never come to me and I never see them, they never see me. Okay, so this part, I just don't care. That will be important eventually, because if you, for example, have this infinite rooted graph, and now you do percolation on it, then you might again get disconnected components, and then you have to throw them out. Okay. So this little issue is sort of, I didn't draw it just to confuse you, because maybe there was originally a connection here. And this thing was really distinguishing the two graphs. But now you do percolation and this piece is disconnected. And these others are still infinite, and now they look the same. Okay, so that could happen. So now we still have no randomness. Okay, and I, for the moment, still don't want randomness. Okay, so now let GN. The sequence of not necessarily, okay, possibly disconnected deterministic graphs. Okay, so let me draw a few first. I will take union union. Let me see how many triangles. Okay, so Gn 3 triangles, not big Gn, just this one. Okay, so that's one thing you could think of. The other one would be a little piece of the infinite square lattice. Okay, so this will be maybe it's the side chunk of your word. But in addition, so this is now in the language of physicists, a cubic centered lattice. And now what I do with this, so imagine your favorite deterministic sequence of graphs. And for finite graphs, but whose number of vertices goes to infinity. So now I will choose a root ON uniformly at random. Of my vertex set. Okay. So what does that give me? Can you still read it down here? So this gives me now a rooted random graph. Okay. So this is, okay, if I fix this, this is just an element of my possibly infinite rooted random graphs. So this is an example, right? So if I put a point here, you get some rooted graph. It's not infinite. If you put a point somewhere here, you get a different rooted random graph pretty soon, as that distance is larger than 1. If you choose this as your root, you get another rooted random graph. Okay. And so if Pn is the distribution, okay, so this is just a uniform distribution over your vertices, then I will say definition Gn is locally weakly convergent if and only if exists a measure mu over our space of infinite rooted random graphs such that the expectation with respect to, there's no randomness except for the randomness you put on by looking at a random root. So the expectation with respect to this randomness of any function of your graph. Okay. So this could be, for example,
Sorry, continuous. No, any continuous.
I haven't yet said for all f. Okay, the for all f comes.
What you said, any function.
Such that. Okay, so just for the moment we define that for any function. Okay, so this should convert to the expectation with respect to mu if you calculate this function on the graph sigma g. I really want to be sort of mathematically consistent there. Sigma g should be drawn from that distribution. So let's see, okay, for all f from your set of possibly infinite rooted random graph into R, bounded and continuous. Okay. So roughly speaking, you can just think of the function f as only depending on balls of a certain radius r, but you should allow this radius to possibly grow to infinity. Yes?
So if it is convergent, then does the limit exist? So
That is my definition. It's considered locally weak convergent if there exists a mu such that this holds. Okay. So let's see what that means in these examples. Okay, so what do these examples converge to? This example
Question.
yes.
Is it true that for finite and the graph it should be finite? Wait,
Deterministic graphs such that okay, so we have a growing sequence of yes, you need finite graph because otherwise I wouldn't know what a uniform random convergence is. Okay. So let's look at these examples.
Christian, can I ask you a quick question for motivation?
Yes.
What kinds of, once we have the definition, what's like the killer app of the definition?
Okay, so let me step back this before I should probably have done that before. So this notion of locally convergent is a way to define the limit of sparse graphs. Okay. And it turns out that, so Wiek hinted to that in his talk. Okay, so if you have a sequence which is locally convergent, maybe the limit is a tree. Okay, or maybe the limit is a random object, a branching process. Okay, and now you might hope that your sequence of graphs is, well, so if this sequence is actually deterministic, okay, it's not very useful unless you start to study processes on it. Okay, if you don't study processes on it, it's still useful, but then it's only useful if you have random graphs. So assume I have some sequence of random graphs like G and P. Okay, and I wonder, does this sequence have a giant component? And to decide that, it turns out that he gave us a criterion which he didn't define, which I haven't defined yet, because I haven't defined for you yet what we do when the sequence is random. But when the sequence is random, you could ask, is there a giant? Okay. Now, is there a giant is not a local quantity, because if I fix any finite radius, you can't distinguish whether there's a giant or this thing has size square root of n, right? But you might hope that in certain situations, if for each r, you see a ball of radius r, which is not stopping to grow with r, maybe there is actually a giant in your graph. Okay, and it turns out there are techniques, and it allows us to sort of tease apart the local properties of your graph, and those are usually not enough to guarantee a giant, plus the global properties. And there are many things. So for example, if you want to study random walks on that because you love rumors and that is sort of maybe your model for rumors, again, you might wonder, once it spreads local, will it spread to the whole graph? And or you may want to say, well, if I study it local, G and P looks sort of like a tree locally. What if I do my statistical physics on that tree? Will that actually describe correctly statistical physics of my sequence? So you can ask all kinds of questions like that, and sort of can separate out. There may be some properties for all what you need is this local notion. And there may be other properties where it's not true, where you need more. Okay, so this will distinguish us from the dense graphs, where once you had this convergence of these probability distributions, you got a graphon, and once you had the graphon, you could calculate statistical physics and cuts, and you can actually calculate percolations on these graphs. So for the dense graphs, a lot of processes on these graphs are determined once you have convergence. For this local notion of convergence, there are some processes which are determined and others which are not. And I will so I'm doing, unfortunately, the boring math and just bringing you up to speed to the math which we sort of need and which Suvik was putting under the carpet there somewhere. And Yegane may sort of now put a little less under the carpet because she has that at her disposal. So, but I still want to ask you this question because I think it's important, okay? Yes?
For that, you said for any L or F function,
Yes.
that is continuous.
That's continuous with respect to, right, with respect to the local. Okay, so what does that mean? That means if two graphs are similar in very large balls, if they are isomorphic in very large balls, then the value of the function shouldn't change too much. And in many cases, the only way to prove that the function is continuous is actually to show that it doesn't depend on the ball anymore at all once R is big enough. So for example, if I ask whether the component of a random, so I look at the vertex, I look at the component of that vertex, I ask whether it's bigger or smaller than 500. Well, you can convince yourself if you were in a bounded degree graph, then to be bigger or not than 500, you can sort of, well, once you have, well, actually you don't even need bounded degrees. Once you have gone up to distance 500, you will know whether it's bigger than 500 or not. Okay, because either you have found 500 vertices, maybe there are much more, but anyhow, if you have at least, if it has 500 vertices, you have either seen them at smaller distances, or you have walked up to distance 500 and you know that. So if you have walked up to distance 500, 499, and you see only up to 499, right? So you see less than 500 vertices, and at distance 500, you don't see a vertex, then you know the component has size smaller than 500. So the question whether the component of the root of a graph, so and input here any graph, so if you fix some GN, you fix this. And now the question whether the component of that vertex in this graph has size at least 500 is the local function. So many of the things, right? And maybe you actually know you have some function which you can approximate where you sort of, right, you could ask, is there a vertex at distance 500? If so, I give it value 1 over 500 or something. So you could obviously construct continuous functions that depend on all distances. But they will actually sort of be generated by the functions which just depend on finite balls.
But this isn't continuous. You're saying the function 0 and then a step function at 1? Like,
in this metric considered continuous.
So you are saying that if D log is sufficiently small, then the F function is closed, arbitrarily closed.
Yes. Okay, you want me to define, so F is continuous. For epsilon axis to delta, such that if local reduction prime smaller equal delta, then F of this minus F of that smaller equal than epsilon. Right, so you want this to, so if this is sufficiently small, this gets small too. Okay, good. So now let's go to these examples. Okay, so I choose a random root here. And now it turns out that in this case, the limit, the mu, is actually not random, it's a deterministic limit graph. Okay, in that case, the limit graph is just, I can take one triangle, put the root in it, And that's a limit graph. It's a rooted triangle. Okay, so even though you have this infinite sequence of graphs, when you choose a random root, it will lie in one of the triangles. And then you see the triangles, and since we delete the components which are not of the root, that's your limit. Okay, so that's example 1. What do you have in example 2? In example 2, I just have ZD, well, in this example, Z2 and the origin. So you have sort of the origin. So you get just, so here the limit is an infinite graph. It's rooted, but it's still not random. Okay. Now it's different in this case. Okay. Because in this case, with probability 1/2, your root sits here. Then you have degree 4. And with probability 1/2, it sits here. And then you have degree 8. So that's certainly different. So in example 3, with probability 1/2, you get this guy centered in the middle of one of these squares and going off to infinity. Okay. And in the other case, you get, that's too low, you get this point as your center. Okay, and here the root has degree 8.
In both cases, the edge effects are not part of the limit.
In both facts, you have an infinite. So in both cases, so this is sort of, I don't know how I want to call that, ZD face centered with this root, right? And here you have this root on the same Z2 base. I don't know cubic centers. What is this usually? Anyhow, I call it cubic centers. In 2D makes no difference whether it's face centers or cubic centers. So you just add this, right? So this is an infinite graph. And with probability 1/2 it's this, and it's probability 1/2 it's that. Okay. So if you are so for example, your function could be, I look at such an infinite graph. I look at a ball of radius 5. I do percolation on that ball of radius 5. And I ask you whether that component has size at least 3. If that would be your function, well, depending whether you sit, if you are here, the probability is sort of smaller because you only have 4 connections to go out one, whereas you have 8 here, right? So the function on this graph has some value. On this, it has a larger value. And the expectation with respect to mu would actually mix it. Okay, so, but I'm already sort of talking about, this is again a motivation which we have not quite formalized, but just for motivation. Okay, so, but these examples you should keep in mind. So far, so is it roughly clear what it means for a sequence of finite graphs to be locally weak convergence? Yes?
Okay, so in the finite graphs, those were finite graphs with edge effects, right? There were some weird.
Yes.
But the point is that those are a negligible share of what's going on, so they don't show up in this.
Right. Okay, but if your finite graphs would be, if I would have a sequence of finite graphs, this graphs, and then sort of have a line which goes to infinity,
Right.
then these edge effects will remain. And now it will matter whether the root is here or here or here, even though maybe then these I make infinite and just make the edge effect go away, right? So you can have a sequence of graphs which has some edge effects, some of them go away, some of them stay. It's all allowed in this game. Okay, so it allows you to ask questions. You have an arbitrary sequence of graphs, and now you may want to know on that sequence of graph, what's the probability that if I start to do my economic game at the origin, what's the probability that it will reach equilibrium in sort of this finite graph? And then you may want to ask, what's the limiting question? And then may you want to know, is it enough to know this limit, or have you lost information which were in the finite graphs which were actually important for the effect you wanted to study? So that's exactly sort of the kind of question you want to study with local weak convergence. They sort of, and you should really keep in mind they're sometimes useful and sometimes you need extra conditions. So now we have to, how I'm doing on time. I have still time. Good. So now we have to discuss what happens if your graph itself is random. Okay. And now things become confusing. Okay. So let's say, and let me first give you a definition which is a possible definition, and it's sometimes used, but it's not a useful definition. Okay. It's actually a definition, it's actually well defined, but that definition will not be very useful if you want to prove things. Okay. If Gn is random, for example, GNP, or D-regular, D, which is D-regular. Okay, so I have two examples here. And for example, let me just put two different examples. I can put here Gn3, but I could also put, oh, there's no 3 regular infinite lattice, huh? So maybe it will come 6 regular. I just thought, nice, I put a triangular lattice, but unfortunately it's not 3 regular. Okay, so we could look at Gn6 or this graph. Okay, and we could sort of study the weak local limit. Okay, so this is random, this is not random, but here we choose a random root. Okay, and as it will turn out, even with the randomness, and no matter how you define randomness, they will have the same weak local limit. And this guy is an expander, and this one is not. And they in many ways behave totally different, but they will have the same local limit. So, but just keep these examples in mind. Okay, so if Gn is random, I define Gn is locally weakly convergent if and only if I have that, again, for all f is bounded, the expectation, and now this is with respect to the randomness of Gn and Xn uniformly at random in the vertices in Gn, okay, of f of the random root and Gn converges to the expectation with respect to some, so if they exist, measure mu, and actually I will call it mu bar, such that this converges.
Christian?
This shouldn't be this. I don't care in which order, it's expectation.
Yeah, so Gn is given now.
Gn is random. It's
And then
a
you
three
choose a-
regular random graph.
Right.
Then you choose a random root.
Right.
But you could also first choose a random number from 1 up to n and then form your Gn, right?
Yeah,
So
yeah,
in that case, but you could imagine that the graph even has a random number of vertices, and if so, I have to first choose Gn randomly and then choose a random root in it, and then I take expectations with respect to both, and then I ask whether this converges. Okay. Now, this actually, if you really think about it, okay, I can tell you why it's sort of not a good enough notion. It guarantees you convergence of first moments. Okay. And first moments will not give you concentration. Now you might have said, wait a second, so that's actually an issue here already. Why would that ever be useful? This is also a first moment condition only, right? It's just first moment with respect to the random root. Okay. And so you might actually worry how useful this is, because again, it's only first moment, but actually this one happens to be, so this is your standard notion of weak convergence with respect to this topology. And that's just how weak convergence is defined. You take expectations with respect to continuous functions, and that's sometimes quite useful. Okay. You wouldn't want to ask much more here, because then you would certainly not have many examples which are at all convergent. Okay, this is sort of pretty much for these local notions all you can ask for. And so it turns out, okay, so we can ask this, okay, but we can formulate a different condition. So if this would be my definition, okay, and so weak would have used this definition of local weak convergence, then actually his theorem would have been false. So yes?
Can you restate this weak convergence definition in terms of convergence in distribution?
I sort of probably knew that at some point.
Yes, we can do this. You know? For every fixed finite rooted graph H, and for any
sure.
distance R, probability that the ball of the first graph is
Yes.
isomorphic to that particular graph converges to the probability that blah, blah, blah.
Correct. By sort of, so that is a, but this is not the notion of convergence in distribution, which is this,
Using this.
because that would mean the distribution function. Legane, do you remember?
So there is, to me, usually this looks like kind of convergence distribution.
Right, this is, you see this, it is what, so you want that the distribution, you see, this is not, this just says that the expectation of f of this is not the same as saying that the distribution of this converges to the distribution of this. Because actually, well, that's just not true, because the distribution of this does often not converge with this notion of that. You sort of, right? I mean, you have to somehow bring in your local, you have to sort of somehow use the d-local, right?
Yes, that's what I'm saying. For every given.
Right, but what you define is not convergence in distribution.
I see.
That's not for random
Yeah. It's not for random graphs.
Yeah, so for random graph, you have to condition on the graph.
Exactly, yeah.
And then say that the whole almost should.
Right, no, that is again a no. I mean, okay, so there is notion of convergence which is in probability in distribution, almost surely. There are many versions of, so this is weak convergence. Is still another notion of convergence, and depending on your situation, there are sort of different notions. So I mean, Peter is probably our expert. Is that the same as convergent in distribution?
Well, the question is like, what distribution do you want to converge, right?
Right.
The problem is that in this local weak convergence thing, randomness is kind of. So you asked earlier what killer app is, right?
Yeah.
When you come at that from a modeling point of view, it's like this is somehow frustratingly less useful for inference than fitting a stochastic block model, because you don't have this kind of summary object, right? It's more like it's somehow more descriptive. And basically the split in the randomness that you get by drawing the graph at random and then drawing from the graph line, that somehow splits randomness into two big parts. And here you're splitting off almost nothing in a sense, because you first have to generate the entire graph and then you randomly pick a root, right? And so I think we have to ask here, like, what exactly do you want to converge? Do you want the distribution of the graph and then you want the whole thing to converge? Or do you want
So I will just tell you, so will be three notions, okay. And so this is one, and this one turns out to be just not useful, okay. And to say in distribution, as we said, we would have to talk which distribution, and that will actually, that's exactly the confusion. Now the question is with respect to this or with respect to this. I mean, you could just say, okay, for example, do I need the distribution of Gn to converge? Well, what does that mean even, right? Or do I need the distribution of this rooted random object to converge? I will, and that is actually not the same. It's sort of, so it's, so anyhow, I define it local weak convergence, which means that if you integrate with respect to a continuous bounded functions, those converge, okay? So that's weak convergence. It's not weak star convergence, really traditional definition of weak convergence in probabilities. Weak means just under the integral, okay? So, and if you have delta functions in your life, right, you always have convergence under the integral.
Christian, can we just say in general, sorry, that the weak here, meaning that weakest ever possible among all the convergence notions we know from probability?
Look, this one, okay. The whole community defined local weak convergence like that, okay?
Yeah.
Aldo started that business, so I actually might prefer to just call this Benjamin-Schramm convergence.
Yeah, me too.
But the community calls it local weak convergence, which means with respect to the local metric, it's a traditional notion of weak convergence. So it's perfectly fine for probabilists, okay? And maybe it's not fine for a statistician or somebody who wants to do machine learning or so, whatever. It's a definition. And it's actually not a useful one, even though some people, so this is just a nice definition if the sequence of graphs is not random, but if the sequence of graphs itself is random, this turns out not to be a useful definition. Okay, so what is this issue? Okay, so the issue is that if I look at sort of the limit of n goes to infinity of E, let me now just choose a random root. The formula at random in. Now I calculate a function which depends on the random root and the random graph. But this object is just still a random quantity. And that is sort of the thing we really have to worry about. For example, you have a graph, okay, let's you do percolation on it, okay? And now you ask, what is the probability that a ball of radius r has sort of sees at least 500 vertices, and r is 20, okay? So if your graph is random, this is a random quantity. And if you but if, for example, your graph is with probability half, a union of disjoint 6 regular graphs, and with probability half this hexagonal lattice, okay, then you will never get with probability 1 convergence of the size of the giant, because in one of them, the giant will be this small 6 regular graph, And in the other one, the giant will become a giant, okay? But in expectation, you will not see the difference up to that distance, right? So there will be notions of graphs. I can, for example, if I have a sequence of graph which converges. I take 2 copies of it. Well, you choose a random root, let's say they have the same size. With probably half it sits in one of them, with probably half it sits in the other. Since they are the same graph, I may as well just say, okay, I have a random root in this one graph, and the limit is some limit locally. But in one case, the giant component will be half the size of the other, okay? And this will be totally hidden in these expectations if I take here also the expectation with respect to the randomness of the graph. Okay, so I don't want to take so this is a random quantity, and we could, for example, instead of asking take the expectation, so this is a random quantity even in the limit. So, and now what is the limit of a random quantity? I haven't even defined that for you. Okay, what is well, the limit of a random quantity could now be in distribution, in probability, in almost surely. Okay. And so I think the convergence of this object in distribution is probably the same as the weakly log convergence. Okay, so to your question. But we will not be interested in that anymore. If the expectation of this converges, I will just call it locally weakly convergence. So now I can sort of say, okay, what if this converges in probability? Okay, with respect to, let me express, with respect to the randomness of your random. So this was random with the random root and Gn. Now I integrate out, okay, so let me write this explicitly. This is 1 over V of Gn, sum over X in V of Gn, F of X and Gn. So this is clearly, if Gn is not random, not a random quantity. I have integrated out the randomness with respect to the root. And now this has still this randomness. And now I can ask that this converges in probability to mu of F of sigma and G. This graph is drawn from this distribution. Okay. Or I could ask that this converges almost surely with respect to V of Gn, assuming I have coupled all the Gns just for the experts. So these are 2 different notions, okay, and both are actually useful, okay. Because if you, for example, study percolation and you have all the other conditions which he has, and you actually, so if you use his theorem with this definition of local weak convergence, then actually his theorem is false. Okay, because he actually has, then you can prove maybe that the expectation of the giant is something. I know even that doesn't work. So you just can't, so it just is not useful. If you have this condition, okay, then actually if this converges in distribution, then the second moment of this guy will also converge. And then you can do second moment arguments and prove the concentration of the things you in the end are really interested in. So having convergence in probability of this object is useful. Convergence almost surely of this object is also useful. Having local weak convergence of this object is in most cases useless, unless your sequence itself is non-random, in which case they're all the same. Okay, so these 2, so these are called, and I'm using the notation of Hofstadt graphs. Is it called random graphs? It's called large graphs.
Random graphs and complex networks.
Random graphs, complex networks. And it's really important. You can sort of make tons of mistakes in this area proving theorems which are just not true if you are not aware of this subtlety. Okay, so these are called local convergence in probability or local convergence almost surely. Okay, for the two versions. Okay, and so if you want to prove, and so for example, there's an interesting fact which I will just tell you. If you have a sequence of random graphs which is locally weak convergent in probability, and you do percolation on it, then the percolated graphs are also convergent, locally weak in probability. Okay, and that gives you second moments for free, essentially. So this turns out to be super useful. Once you have proven that your sequence is convergent, so in many, I mean, you have to do the math to see, but in many applications, it will essentially give you concentration with respect to the randomness of these graphs for free. Okay, and if you do this definition, it just gives you nothing. So well, it gives you some expectations, but often you're interested in the expectation of some global object. And just because you have expectations of local object doesn't mean you will get expectation of the global object. But if you have sort of concentration for these local objects, let's say you had almost surely that you can use this theorem because you have almost surely, and then you can actually then conclude something in the end about the giant and also about the expectation of the giant. Okay, so that I really, this is sort of more important than anything else I want to say to get really across that this difference. Okay. So are there questions about these definitions? I think you should sort of, to see how it really works, maybe, I don't know whether you will see, Yegane, do you think they will see in your talk a little how this stuff works? Well, they certainly should see how it's useful.
Yeah. I brushed over how to use
So let me tell you, for example, if I know a sequence is locally weak convergent, no, that's theorem is actually too more general. Okay. I just want to tell you a theorem which holds, but it's actually is true general. So I wanted to say, if you have a sequence which is locally convergent in probability, you will know that two random vertices, that their distance must go to infinity. That actually happens to be true in that notion. Okay, so that's one of the few useful results which actually hold in this general setting. Because, well, if something goes to zero and expectation goes to zero and probability too. So it's always, there are certain things which are useful, but in most cases, and the way you prove this usually, okay, is you just choose two random vertices in your graph and then prove that the expectation of the product of these functions converges to the expectation squared of the original thing. And that is how you, right? Because now you have a random quantity. How do I prove it converges in probability? So you do a first and second moment thing on that in the very beginning for your graph sequence. And then for many of the questions you're interested, you don't have to worry about concentration anymore. So that's why this is a very nice technique. And Remco, in his book, where he really wanted to apply it to studying the giant, really worked out these differences, which for the probabilists who sort of start this is in a very abstract setting, and they use the symmetry of the limit object, and then they prove some very nice general theorems, they don't even see that there is this difference because they have these nice theorems, which they could all probably prove for the other version too. And then actually, if you write a paper where you do that careful, they don't read it careful and they say your paper has a mistake because I have a counterexample. And that's because they never think about this difference. And that is the counterexample would be there if you use one definition, not in the other. So when you actually want to do applications of that, these notions are really different. And I think it's really, Remco should be really credited for really pushing that difference.
Sounds like something from experience.
Huh? But for example, we a while ago showed that the preferential attachment graph converges locally weakly. Okay, and then we claimed some theorems. Okay, but actually, now it turns out that our proof could immediately use to also prove that version, but we didn't do it, right? And now we claimed some convergence of power laws and things like that. So strictly speaking, this paper is wrong. Okay, which I hate to admit because I like finding mistakes in other people's paper, not in my own. And actually, I like to find them myself. But anyhow, actually, I did find it myself. We found it together. And it's easy to repair in some cases, it's easy to repair, and you just do your second moment bound to prove the convergence. In other cases, it's actually not easy repair, and you just have a theorem which is false. Okay. Yes.
So just wondering if you have just this condition without the probability convergence. So can you at least conclude that expectation is positive? Expected
Of the giant?
Yes. Not the probability convergence. That
no, I don't even think that false.
Okay. So this condition would give you that expected number of vertices in components of size larger than k. Proportion of that converges in expectation. Yes.
In expectation with respect to your random graph, right?
But I mean, I was just wondering if there are counterexamples if you consider linear graph. I mean, I'm not claiming that expectation converges to some constant, but does it stay bounded away from zero? So if I
know what you're saying.
So there will be counterexamples there as well.
I think so, because I could imagine sort of mixing in some graphs of size
Square root
n stuff where in expectation it doesn't show up, and you sort of but it's not with probability 1. So I actually think, I mean, truth of the matter is, so either you're sort of a real mathematician and you want to prove a general theorem, and then you may make mistakes if you do that wrong. In real life, you have very good intuitions. And even though you may only prove that, your intuition tells you, oh, this thing is probably almost surely convergent. And maybe you can't prove almost sure because that's very hard to prove. And that, I think, is a very nice of this thing. But often when you're just willing to do more work, you can calculate the second moment. So you should be, if you can prove this version and the other one is not true, something very weird is going on. But I'm not sure if your random graphs are spin glasses and things like that. I mean, there may be situations where this delicate, I mean, we know from statistical physics, there are situations where it's just not true, you can take expectations. Okay, and this is an example where at least so anyhow, this is the general setup. So let me just mention the symmetry, and I will not do any of the other stuff because I think this is really abstract. Well, maybe I will spend one slide, but so what is the symmetry? So assume you have this limit, okay? Are there any symmetries, okay? It's not very clear, right? If your original graph had a symmetry, maybe that symmetry is there, right? If your original graph had all degrees are 3, that's a symmetry. Well, it will be true in the limit, okay? But that's not what I'm talking about. I'm talking about exchangeability or some symmetry like that. So there's one symmetry, which comes from the fact I choose a random root in my graph originally. Now imagine looking at the neighbor of that random root, okay? So that neighborhood can't be arbitrary, okay? So for example, if I choose the neighbor of a random root, that neighbor can't have degree 0. So I could have a sequence, I could have a graph, okay? So this is my graph. So with probability 1/4, I see an isolated vertex. So the limit of that is with probability 1/4, I get this, and with probability 1/4, but 3/4, I get a rooted triangle, okay? Now, if I choose a random neighbor of my thing here, that random neighbor will have degree 3. So if I look at, so the distribution of this guy can't be, so the distribution of a random neighbor of the root can't be arbitrary. In particular, it must degree larger than 1, even though the root doesn't have degree. So the question is, are the two related in some reasonable way? And the answer is yes, because in the finite graph, if you think about it, the probability of choosing a random neighbor of a random root is just choosing probability proportional to degree. So in other words, the limit must be such that if I look at my distribution on infinite graphs, I choose one, I take the root. Now I look at the distribution I get of the graph seen from a random neighbor of the root, still infinite. Then this distribution must be the same as my original distribution, reweighted by the random degree of the root I'm currently seeing.
And friendship paradox.
Yes. And so this is called, what is it? I always forget the word. I'm sort of not.
Unimodularity.
Yes, unimodularity, thank you. So it's called unimodularity, okay? So every limit object must be unimodular. And the question whether every unimodular random graph actually can be obtained as a limit is open.
Sorry, what's the definition of unimodular?
Just this thing. You have an infinite random graph, rooted. And if you look at the distribution of the graph obtained from that by taking a random root of the neighbor, that gives you a different distribution. I mean, it's the same infinite graph, but it's a different random rooted graph. And you should get that distribution by just choosing your vertex according to the degree, right? So the probability that G of sigma. Okay, so I define G star, sigma G star, okay. I define it by choose sigma prime and G from mu, then choose sigma uniformly at random from its neighbors. Sigma prime. And now look at the rooted random graph where rooted at sigma. Okay. So this is some distribution mu star, which is different. And the claim is mu star of, let's say, I want to look at some ball of radius r around the origin. In my graph. Okay, so this is equal to mu of BR of sigma G times the degree of the root in BR, well, this being equal to some graph H, so the degree of the root in H normalized. Okay, so that's a very, yes?
There's a different view to look at this.
I know there is a very different view, which is mass transport on your graph and stuff. Huh?
I mean the lines and Trump kind of, so basically you think about doing simple random walk on your graph and looking at the scenery that you observe that remains invariant, basically. So it's kind of like stationarity, but it's kind of a messed up stationarity because the shifts that you're allowed to make depend on the instance of your graph, on the realization.
So that's the original definition by.
No, that's the later. It's the lines implicit in, I would say, the lines from this New York journal.
Right, the lines. Okay. So there's also another one where you can sort of talk about transporting mass in your graph, and this is essentially doing that in one step. And once you can do it in one step, you can do it. This random walk one, I'm sort of astonished that it's not originally in Benjamin Schramm, because they actually studied random walks on limits and what it says about the random walks on the original.
Just think about of scenery, I think, right?
Yeah.
We're just looking at triangulation.
Whereas the more, so in the literature of the last 5 to 10 years, this has been used a lot to study percolation graphs. And it has, in the end, simplified some of the existing proofs of the giant. Goes in the literature as is percolation local. Which is the question once you know sort of you have a local limit. Assume you have two graph sequences and they have the same weak local limit. Do they have the same PC? Do they have the same size of the giant? Questions like that. Okay. I think I'm out of time almost, so let me just put up a little. So I would like the screen for 1 minute. Hello? Is it back? Great. Okay. So it turns out, okay, so we can again define these different notions of convergence. And if you don't have bounded degrees, you have to modify them a lot. So let me just, for the purpose of this talk, not discuss it. And it turns out that this one is again equivalent. Okay. You just have to normalize your subgraphs correctly. So here now you can normalize by 1 over n as you suggested, either you or you. One of the two guys in yellow shirts suggested to normalize different. You can also define convergence of cuts and free energies. You again just divide by n instead of n squared. But it's not true anymore that these things are equivalent. I will not walk through all the counterexamples. So what you have actually is that if you have, so this is sort of, I call it here left convergence because you test again your graph from the left. So this local weak convergent for a non-random graph and the local convergence in probability and things like that. So, but let's say we were a deterministic graph. This does not imply convergence of statistical physics. It does imply statistical convergence of high temperature statistical physics, because high temperature statistical physics is really local. But it does not imply, for example, convergence of, I call this quotients. I should have said multi-way cuts. Quotient is an even generalization of that or a different framing. So it does not apply convergence of multi-way cuts. And there are easy examples. You take a deregular random graph and a deregular bipartite random graph. Their cuts, their max cut differ by a factor of 2, essentially. But they have the same weak local limit. Okay. So this does not imply the same cut. So it doesn't imply global properties. On the other hand, but if you have right convergence, you have in particular high temperature, high convergence. And for high temperatures, actually these two are equivalent. Okay, because high temperature physics, to some extent, if I have high temperature physics for all possible models, I see sort of the local interaction, which means I see the local graph, sort of distance 1. And then if I expand my things out, further interactions, the interactions will go on and on and on. And so you have this direction. And together with David Garmanik, who seems, I don't see him here, we actually came up with a notion which is some notion of large deviations, which actually implies all three. Okay. But that is maybe not that important. I think it's actually more important to just remember that. And this is again the same thing. So if you have this local convergence and you have an extra condition for statistical physics at high temperature, then it's useful. In general, it's not, because you can come up with counterexamples that look globally different and locally are the same. And if whatever you do, test globality, and it always depends on what global and local means. For percolation, for population epidemics, it's one thing. Turns out that you need, in addition, expanders. For statistical physics, expander is not the issue. For cuts, that's also not the issue. It's the issue whether you're, for example, whether you're two-color, it depends. If you take a torus of even or odd side lengths, so they are very different for two colorings. But they have totally same log vehicle limit. So that and they both are not expanders. So it's not always expanders, okay? So, and it depends on, sparse graphs are just very complicated, and sort of a lot of complexity theory uses sparse graphs for counterexamples and things like that. And so we can't really expect that there is sort of this global theory of sparse graph convergence which answers all questions. You have to sort of work. And Jäger has done a lot of work, and she will present some of how we can actually use this stuff this afternoon.
It seems like the old speakers have prepared excellent slides. Will all these slides available? Because it will be very educational.
I don't have slides here. Did you
Viewer
take?
and ease and
No,
everything.
no, these are not slides.
No, I have taken care of it
Oh, so
myself.
you will type it up in
No,
text
no,
and
no,
then
no,
you
no,
can
no, that's
post
not what
it?
I'm saying. Your slides, I think, Tom.
But I have
you
given my
also
first
sent your-
slides already to the, so send them to Elizabeth, and she will annotate your talk with your slides.
Excellent, well, very good. Thanks, thanks. Good, because also you yesterday,
Because I guess we have the videos, but.
video or slides will be also useful because it's static.
Yeah.
You may want to just you may, when you want to look something up, not have to walk through an hour entire.
We can read them.
Or maybe we like your slides, but we don't get post-traumatic stress when you hear your voice for some reason. Or mine. Because all my jokes are so dumb, so you don't want to hear them. So it's nice to have the slides. I sometimes like to just look through slides and not through a video. But
Yeah.
maybe that shows my age.
Integration.
So we both are sort of, you probably prefer watching the video. I'm just shooting somebody who's young, I'm sorry.
You're categorizing young and old.
I was saying the two of us, the generation who wants to read slides and not watch videos.
Well, my talk isn't even going to be recorded, so.
Oh, it's not recorded.
don't want to be on the internet.
Oh, you didn't get Microsoft permission to have been recorded?
I have permission, I just want
To be
to
beginners.
create a different atmosphere.
Beginners.
I see. I see.
No, no.
You guys better come in person.
Yeah, we should send a warning on the Slack.
Yeah.
Yeah.
Never happened.
Actually, I just said question.